Hi everyone, welcome to the fifth video of our thermochemistry unit. This is actually the last video, so this is the last new information that you're going to get for this unit. This video is all about the enthalpy of formation and strength of covalent bonds, and we're going to look at bond enthalpy as well. This is sections 5.7, so heat of formation is 5.7, strength of bonds and bond enthalpy is 8.8. So please make sure that you read through that section of the book just to look at some of the example problems, and they're worked through step by step. So we're going to start out with the enthalpy or heat of formation. The enthalpy of formation, which is labeled as deltaHF, is defined as the enthalpy change, remember enthalpy change is deltaH, for the reaction in which a compound is made from its elements in their elemental forms. So the change in enthalpy, okay, deltaHF, is when 1 mole of compound, so in this case 1 mole of water, is formed from its elements. All right, so H2 and O2, because H2 and O2 are diatomic. These are their standard states. Hydrogen is a gas, oxygen is a gas. It has to be for 1 mole, and deltaHF, the heat of formation, has to be from its elements. The heat of formation depends on physical state, so it would depend on if this was gas or liquid, pressure, and temperature. Again, deltaHF heat of formation is when 1 mole of a compound is formed from its elements. So the standard enthalpy of formation is, it's measured under standard conditions. So standard conditions are 25 degrees Celsius, which is also 298 Kelvin, and 1 atmosphere of pressure. This 1 atm has actually been changed to 1 bar, which is 1.013 atm, but we're not going to worry as much about that. We're just going to say 25 degrees Celsius, which is 298 Kelvin, and 1 atmosphere of pressure. The standard enthalpy of formation, like I said in the last slide, is for 1 mole of the compound in its standard state, formed from its elements in their standard states. So if we look at this example right here, carbon's standard state is graphite. So when carbon is an element, if it's in its standard state, that means what it's most likely going to be at these standard conditions. Carbon will be graphite, hydrogen will be H2 because it's diatomic and it's a gas. Same with oxygen, it's diatomic and it's a gas. So these are their most stable forms at 298 Kelvin. And then again, the stoichiometry always has to indicate that you have 1 mole of product being produced. When we look up here, notice how it's deltaHF, but then there's this degree sign. This degree sign indicates that you're at standard conditions. So if you see this degree sign, it means you're at 25 degrees Celsius and 1 atmosphere of pressure. The standard state of formation, so deltaHF, and this degree sign is known as naught, NaUGHT. So we would say this is deltaH naught. The standard state of any element in its most stable form is 0. So, for example, the heat of formation of carbon here as graphite is 0. The heat of formation of hydrogen gas is 0. The heat of formation of oxygen gas is 0. So, deltaHF of any element in its standard state is 0. These values are actually calculated in Appendix C of your textbook, so it's page 1100. So what I would recommend doing is getting a post-it note or something and putting it in Appendix C, because you'll be using these values in class as you're practicing. One more thing with standard conditions: if you're working with solutions, standard state is 1 molar. So if you're working with solutions, the standard state is going to be 1 molar. So table 5.3 in your book shows some standard enthalpies of formation at 298 Kelvin, but again, even more of these values are given in Appendix C, so make sure you bookmark that. So we're going to look at how this is actually calculated, how we look at deltaH from heat of formation. So we have propane combusting. So imagine this reaction occurring in 3 steps. So the first thing is propane has to decompose into its elements. So in order for this reaction to proceed, propane needs to decompose into just carbon and hydrogen. And then we have CO2 being formed. So we use the carbon from the propane, we use some of the oxygen to form the CO2, and then we form the H2O with the hydrogen and with the rest of the oxygen. So we actually are just breaking everything down and putting it back together. And so what we're doing here is we're actually creating a step-by-step process to where we can use Hess's law to calculate the heat of reaction. So all of the steps together look like this. So we've decomposed propane, and then we've formed CO2, and we've formed H2O. And remember I said heat of formation. So these second 2 reactions actually show the heat of formation. Notice though that in terms of the second and third reaction, heat of formation has to be for 1 mole. Well, here we have 3 moles and here we have 4 moles. So remember, if this was delta H and it's supposed to just be 1 mole, we multiplied it by 3. Same with the H2O, it should be 1 mole, we multiplied it by 4. That's still, we still take that into account when we're looking at the heat of formation, because we can use Hess's law in this way. So if we want to calculate delta H of reaction, what we can actually do by looking at heat of formation is we can take the sum, okay, this sigma means sum of. So we can take the sum of the heat of formation of products. Okay, this N is the coefficient. So we'll look at this when we actually look at the calculation. So we take the sum of the heat of formation of products minus the sum of the heat of formation of reactants, and that actually allows us to calculate delta H. So looking at the example from the Hess's law. So we had propane, we have oxygen, we have CO2, we have H2O. So remember, I said we take products minus reactants. So we take our coefficient, so 3 times CO2. Okay, so we have 3. This negative 393.5 is found in Appendix C. So you look in Appendix C for CO2 gas. So 3 times the heat of formation of carbon dioxide plus 4 times the heat of formation of water minus, now we add up our heat of formation of reactants. So 1 propane times the heat of formation of propane plus 5 times 0. Remember, this is 0 because oxygen is in its standard state here. That makes it easy when we're looking at some of the heat of formations. Whenever it's in its standard state and it's an element, it's 0. So we can actually multiply this out. We add up our products, we subtract our reactants, and we find that our delta H is equal to negative 2,219.9 kilojoules. This is using the heat of formation. We're using the stoichiometric coefficients to find the heat of reaction. So this is the third method to find delta H. We've already talked about calorimetry, we talked about Hess's law. We can now use the change in enthalpy based on heat of formation. So delta H naught of reaction is equal to the sum of the heat of formation of products minus the sum of heat of formation of reactants, taking into account stoichiometry with N and M. And this is on your equation sheet. You just need to know how to use it. So let's look at an example. This says to calculate the standard enthalpy change for the combustion of 1 mole of benzene to CO2 and H2O. And then B says if delta H naught of reaction for combustion of 1 mole of propane is this, compare the quantity of heat produced of 1 gram of both propane and benzene. So with A, we need to calculate the standard enthalpy change for combustion of benzene. If you're not sure what to do, I would say start by writing out a reaction. So start by writing the reaction of combustion and balance it. So if this is combustion, we have benzene plus something else. It's actually plus oxygen yields CO2 and H2O. So we have benzene plus 15 halves O2 yields 6 CO2 plus 3 H2O. The reason that we have this 15/2 again is because if you read this question, it says the combustion of 1 mole of benzene. So if I want 1 mole of benzene, I need a coefficient of 1 here. Okay, so now we have our reaction. Now what we need to do is we need to take into account our heats of formation. Okay, so remember, to find delta H naught of reaction, we add up all of our heats of formation of products, taking into account coefficients, subtract all of the heat of formation of reactants added together, and that gives us our heat of reaction. So use Appendix C to find these values. So what I want you to do is find each of these values of heat of formation in Appendix C and write it underneath the balanced equation. And then when you look at that, make sure you focus on O2 here, because this is standard state, right? This is oxygen in its standard form as an element. This is 0. So using Appendix C, what we find, remember, products minus reactants. We have 6 carbon dioxide, so 6 times the heat of formation of CO2 plus 3 times the heat of formation of water minus 1 times the heat of formation of benzene plus 15/2 times 0. You find that your delta H of reaction is negative 3,267 kilojoules. So here we have kilojoules. You could also say kilojoules per mole because all of your values in Appendix C are given in kilojoules per mole. So for part B, it said to compare the heat in terms of 1 gram. So for propane, it's negative 2,220 kilojoules per mole. This is given to you in the problem. So what we need to do is just figure out, well, how many kilojoules per gram then? So we need to cancel out moles and get to grams. So go kilojoules divided by the molar mass. We get 50.5 kilojoules per gram released of propane. We compare that to benzene. So just use the molar mass of benzene. We get 41.9 kilojoules per gram of benzene. So what we find here is propane actually gives off more heat than benzene, so this would be a better fuel. So another example, it says the standard enthalpy change for the reaction of calcium carbonate decomposing into calcium oxide and CO2 is 178.1 kilojoules. Given the heat of formation of calcium oxide as negative 635.5 and delta H naught formation of CO2, calculate delta H formation of CaCO3 without looking it up. So let's focus on this equation right up here at the top, because here is our overall reaction with the heat. So here's the overall reaction with heat. So this entire reaction is equal to 178.1. This is delta H reaction. Right? This is delta H RxN. Here's one heat of formation, here's another. If we take a look at this, remember, heat of reaction is equal to the sum of the reaction of products minus the heat of formation of reactants. So again, we have heat of formation of products added up minus heat of formation of reactants. So plug in all of the information from the problem. Well, they say the delta H naught of reaction is 178.1 kilojoules, right? That's the overall heat of reaction, minus or equals negative 635.5, that's calcium oxide, negative 393.5 is CO2, minus delta H formation of CaCO3. This is what we're trying to find. This is X. So we have the overall value, we have the values for the products, we're trying to find the heat of formation of reactant. So if we solve for this heat of formation of calcium carbonate, it gives us negative 1,207.1 kilojoules. And again, if you need to see step by step for this, if you look, this is an example problem in 5.7. Alright, so again, we have delta H naught reaction, we have heat of formation of products, heat of formation of reactant is what we're trying to find, and this matches the value in Appendix C. So the fourth method to find delta H is called bond enthalpy. This is section 8.8 in your book. Please look through section 8.8. In section 8.8, it discusses bond enthalpy, bond energy, and bond length. So the fourth and final method to find delta H is using bond enthalpy. And bond enthalpy is the energy that's required to break a bond between two atoms. Usually we use the letter D to represent bond enthalpies. So if you see DHBr, that means that's the bond enthalpy, that's the energy that's required to break the hydrogen-bromine bond. The reason that we use bond enthalpies is because sometimes we may not as easily find standard enthalpies of formation of all reactants and products. And so what we can do is we can use these individual bond energies, which have been calculated, to estimate the overall delta H of reaction. When we're looking at bond energies, the reason that it is bonds broken minus bonds formed is because it takes energy to break a bond. So for example, I have this wooden splint, right? It takes energy for me to break this bond. Right? That took energy. Not a lot of energy, but that took energy, which means that is endothermic. So breaking a bond is endothermic, which means it's positive. Forming a bond, okay, forming a bond is exothermic.
Please excuse the interruption. There will be a meeting for any student interested in bowling after school today in the cafeteria. Any student scheduled for swimming in gym class must bring the regular gym clothes. There will be no swimming until further notice. Thank you.
So forming a bond is exothermic, right? Energy is released, well, that should be a negative. Energy is released when a bond is formed. So it takes energy to break a bond. Energy is released when a bond is formed. That's why it's minus bonds formed, right? So bonds broken are positive, minus bonds formed, which are negative. A reaction will be considered exothermic when weak bonds break and strong bonds form. A reaction will be endothermic when strong bonds break and weak bonds form. So that's how you can actually determine if something is exothermic or endothermic. Again, exothermic is when weak bonds break and strong bonds form, because you have more energy being released by stronger bonds forming, and it's endothermic when you have to put a lot of energy in to break strong bonds and you only form weak bonds. So to calculate heat of reaction using bond enthalpy, you're going to use this. Delta H reaction is equal to the sum of bonds broken minus the sum of bonds formed. Very similar to the sum of heats of formation of products minus heats of formation of reactants. The only difference now is it's switched, right? If you remember that breaking bonds is endothermic, forming bonds is exothermic, you'll be fine. So for an example here, we need to calculate the enthalpy of the reaction when methane and chlorine react to form methyl chloride and hydrogen chloride. So the first thing to do is notice that it says calculate the enthalpy of reaction and you're only given a reaction here. Well, that means we're probably going to have to use the bond energies or bond enthalpies. So what we need to do is we need to determine which bonds are broken and which bonds are formed and how many. Okay, so which bonds are broken and which are formed and how many. So the reactants, those bonds are being broken. So here we have CH4. Well, that means we have a CH bond, but we have 4 of them. So we have 4 CH bonds and 1 Cl bond, right? Because it's just 2 Cls bonded together. So we have 4 CH bonds breaking, 2 Cl bonds breaking. And then we have 3 CH bonds forming, 1 CCl bond forming, and 1 HCl bond forming. So if we take a look at this, we have 4 times the bond enthalpy of CH plus the bond enthalpy of Cl. Those are our bonds broken. And then we have 3 CH bonds forming, 1 CCl bond forming, and 1 HCl bond forming. So we take our bonds broken minus bonds formed. So again, these are endothermic, these 3 are exothermic, that's why these 3 are negative. These values can actually be found in section 8.8. So if you look in section 8.8, you'll see a table. If you're given this on a quiz or a test, I would obviously give you these values. So when you multiply everything out, add everything up, our delta H of reaction is negative 110 kilojoules. So what we did is we used our bond enthalpies, or our bond energies, to determine heat of reaction. We just looked to see which bonds were broken and how many, which bonds were formed and how many. Again, delta H reaction is broken minus formed. So we looked at 4 methods to calculate delta H. We looked at calorimetry, both coffee cup and bomb, which we used Q equals MC delta T, or Q cal equals C cal times delta T, along with the first law of thermodynamics, which was Q1 plus Q2 plus Q3 equals 0. Then we looked at Hess's law. Okay? Hess's law said if a reaction is carried out in a series of steps, the overall enthalpy is the sum of each of the steps. And then we looked at heat of formation in this video, where we looked at the heat of formation of products minus heat of formation of reactants is equal to our overall heat of reaction, as well as bond enthalpy, which is the sum of bonds broken minus the sum of bonds formed equal to delta H of reaction. So these are 4 methods to calculate delta H. We'll look specifically in class on how to determine which one to use, and we'll do a lot of practice with each of these for the rest of the week, just to get you practice with each of these different types.